So, welcome to my stream. This is another stream for Exercism's 12 in 23 challenge. I'll this time I'll wait for maybe a few people to join the stream before starting because last time I didn't provide people enough time, I think, to join. So if you're just joining, welcome. By the way, on Twitch, it says that I'm called Cameron Balahan, but that's not the case. My name is Charles. I don't know why it says Cameron Balahan, but so tonight I'm going to do another stream about the C++ language, in which we are going to explore another exercism exercise on the C++ track. Tonight we're going to tackle the exercise known as binary search tree. It's a hard. It's rated as a hard exercise, mainly because there's a lot of code to write, and it involves templates, which are C++ generic types. So my goal tonight is not necessarily to show to make you understand how to implement a binary tree, but rather to showcase some of the tools needed from the C++ language to do so. So hopefully we'll be able to finish in time for 9 o'clock, my time on the east coast of Canada. So there are a few people in the stream now, so I guess we can start. I have the chat open, so if you have any questions, feel free to ask in the Twitch chat. So yeah. So if we go look at the exercise that I want to showcase tonight, which is called binary search tree. So what this exercise wants us to do is that we need to implement a data structure that will be able to store nodes inside a binary tree that is automatically sorted. So a node in a binary tree has three things. It has a value in the node, and it has a pointer to the left node and a pointer to the right node. So there's an example in the exercise instruction. So let's say that if we have a node containing the data 4, which is the value here, and we add the data 2, what would happen is that the value 2 would be stored to the left of the node currently storing the value 4, because 2 is less than 4. So to keep it sorted, we needed to drop it to the left. And then the example goes on to say if we were to add 6, it would drop to the right. And if we were to add 3 to the tree-like structure, what it would do is it would go first to the left because 3 is less than 4. It would end up on the 2 node, and then it would go to the right because 3 is greater than 2. So again, the goal here is not necessarily to teach what is a binary tree, but to showcase how to build one. So let us go straight to the solution and showcase some code. As I mentioned before, in this exercise, we need to implement a class that is called binary tree, and what the tests want us to do is that a binary tree represents one node inside the tree. So to understand how how the test wants us to do this, we can look at the test code. So basically, from this test code, we can see that it creates an instance of the binary tree here with a specific value, but when it creates the binary tree, it uses a template parameter, which is called t here, to create a binary tree for a specific type. So what we need to do is implement a class named binary tree as a template to be able to store any type inside the node. So we'll just go ahead and do that first. So let's declare a template with a type name T, which is the way to declare a template parameter in C++. And we will name our class binary tree here. So this is simply the class. So this would make our test happy when it tries to allocate this binary tree. And the minimum interface that we need to implement for the one test here to pass is that the tree has to have 4 methods. One method called data, which allows you to fetch the data inside the node. One method called left, which returns the pointer to the left side. And one method called right, pointer to the right side node. And finally, a method called insert, which allows you to insert a value inside the tree and trickle it down to the appropriate spot. So what we'll do tonight is I'll try to go test by test and implement only the minimum functionality to get each test to pass, like a kind of a test-driven development approach. Okay, so first of all, let's go inside our node class and declare what member variables we need to implement the node. First, we'll need a variable to store the actual node data. So I'll declare it as type T, which is the type of the template parameter. And let's call it data, or I can call it data like this. Now we have to have members to store the left and right hand side pointers. But using raw pointers is usually not recommended in C++ because it can lead to memory leak if you don't free the pointers correctly. So the best use of this would be to have smart pointers. If we include a header called memory, we get a small pointer that is called unique PTR. And that unique pointer can store one instance of the binary tree. So here what I'm declaring is I'm declaring a smart pointer to a binary tree. The unique PTR class is a very simple smart pointer structure that assumes ownership of a dynamically allocated object that is stored on the heap. And it is automatically, the object that it owns is automatically freed when the unique pointer goes out of scope. So this takes care of making sure that we're not leaking memory and that we're not skipping calling the structures when we destroy our object. So let's declare another one to the right hand side. And that's it for now. Now what we have to do is we have to declare first our constructor. So the constructor that is called here is passed as a value for the node to construct, and that's it. So if we want to do this, we'll write a constructor here that accepts a value of type T. Let's pass it by const reference and call it data. And then inside the constructor, we can initialize the variables. So first of all, we initialize the data variable to the value of the data that was passed in, and that's it. We don't really need to initialize anything else because the unique pointers here are automatically initialized to null PTRs. In fact, to to emphasize this, we can actually write it this way to explicitly say that we want to call the default constructor of unique PTR on our members. Okay, now we have our constructor. It receives a piece of data, stores it in the node, and at first the node doesn't have any sub nodes on the left and right hand side. which is fine. Now we're going to write the getters that allows you to fetch the data and the left and right node as was requested by the test. So first we have to have a method called data that takes no argument and that returns a const reference to the data. Here it is. So in case you are used to reading function declarations in C++, more like this, like const. So the second line that I just wrote is how people use to write function declarations in C++. And the way that I use on the first line here is a new way that was introduced in a more recent C++ standard. It's basically, it allows you to write your return type after the function declaration. And it's, for some people can argue that it's more, I forgot to actually, let me just fix something before I go on. I forgot to actually reduce my screen size. I just realized that. Sorry about that. Okay, that would probably be better. Okay, that's better. So here we declare a method called data, which is a const method, and we return a reference to the data that is inside the node. Because we don't want people to actually be able to modify what's in the node, we return it as a const reference to the value. And why don't we allow people to modify what's inside the node? It's because a binary tree is inherently sorted. So if we allowed people to modify the data inside the nodes, it would unsort the data, shall we say. Now, I have to implement the left and right hand side methods, which will return the unique PTR to the binary tree that is on each side. And at this point, I'm kind of annoyed to have to type unique PTR to binary tree over and over again. So what I'm going to do is introduce an alias. Let's make it public because it will be referenced. So let's say that we're going to define an alias called tree, or let's call it leaf pointer, which is will be defined as a unique PTR to a binary tree. So this declares a new type that's basically an alias for an existing type. So using the leaf PTR name is the name for the new type. So now that we have that new type, we can actually replace the references to the old way of saying it with the new type, which will make it simpler to write. Okay, now that we have that, let's define our our method called write, which will return the right hand side pointer. So at this point, we're only missing one method to be able to compile and run the first test. And that method is called insert. And insert accepts a new value and must insert it at the right spot of the tree. So I'll just first declare the method, sorry, which will accept a new piece of data. And for now, this method returns void. And for now, I'm not going to implement it. I just want to showcase what's going on with this. So now we have the skeleton for a binary tree node. We can create a node with a piece of data. We can access the data using this method called data, and we can access its left and right nodes with those methods called left and right. They return pointers, so actually it can be null. it can be set to null PTR, meaning that there is no left node or right node. So if we compile this, this will compile the code and run the tests. Okay, so the code compiles and the test passes, even though I did not implement the insert method. Why? Because the insert method is not actually used in the first test, because the first test creates a node with only a single value called, which is 4, and it validates that this will create a tree with a single node which contains 4 and has no left or right node, which we've implemented so far. In our code, the code that we've written is good enough for that. So we've got the basic structure of our binary tree node. So let's try to run another test. So in the C++ tests, there's actually a preprocessor directive that comments out the remaining tests. So we can enable them one by one if we just move the preprocessor directive down one test. So now we've enabled a new test. And in this test, it tries to create a tree with 2 nodes, one with the value 4, which is the root, and another with the value 2, that should end up to the left of the root. If we compile that, we'll see that the test should fail because we have not implemented the insert method, which allows us to insert value inside our tree. So the test fails here, saying that there's no left node, which is logical. So what should we do? Here, let's implement the insert method now. So basically what we want to do is, if the value is smaller than the value that we have inside our node currently, we want to go to the left. And if it's greater than, we want to go to the right. And we also need to understand that what happens if it's the same value. The tests actually specify that later, and they want us to go to the left when the value is equal. So what I'll do is I'll do an if here and say, if the value that we have inside our node now is smaller than the passed in value. So if our node if the value is smaller than the one passed in, it means that we have to go to the right. So what do? We check, do we have sorry, do we currently have a right node? If we don't, then we need to allocate a new node and store it in the right pointer. So let's do that. To create a unique pointer, a value that is a unique PTR, we have a helper method that's called makeUnique that actually calls makeUnique. Have to specify the type, so it's a T. Oh no, it will automatically deduce it. Sorry. So you say makeUnique, and you pass in the value that you want to create. Well, that will not work. I forgot. makeUnique, have to specify the type. Sorry, I'm a bit confused. So this will create a new unique PTR, storing a new instance of a binary tree node containing the new data, and store it in our right-hand side pointer. Now, what happens if we already have a right-hand side node? Then we have to trickle down. We have to basically insert that new value in the right node. So what we'll do is we'll say right, and then we'll use the arrow operator, which is defined in unique PTR to return the pointer to the binary tree that is stored inside it, and just call insert with the data. Now, we only need to do one thing now, is put an else here. So if the data that was passed in was equal to or less than the data we have in our node, we have to go to the left. So let's do that. This I won't. The code is essentially the same. It's the same thing as before, but for the left node. So here we have our insert method. It's a recursive method, basically. So you insert a data on the root node, in the root node, and it trickles down by calling insert repeatedly on any node that it encounters until it reaches a point where there's no node. And if when it does that, it creates a new node and inserts it in the tree in the appropriate spot. Oh, yeah, good observation. I'm trying to call make unique with a T here, but it's not the appropriate type. What I want to allocate is actually an instance of binary tree and not an instance of my type. So thank you for the observation. The funny thing is that I actually practiced this tonight's stream a bit by trying to solve the exercise before, and even then I'm still confused and I make mistakes. So sorry about that. Thank you, Mr. Sebenschlafer. Sorry if I'm not pronouncing that right. I don't know how to pronounce that name. Sorry. Okay, so if we compile this, now that we should have a working insert method, the new test should pass, and it does. So all the test cases are now passing. And we can actually see that this is working fine by enabling many other tests. I'll just enable the test up until that point. So all these tests are basically the same thing, meaning that they test what happens when you try to insert values and trickle them down the tree, and they only validate that the tree has the expected structure. So if we compile and run all those tests, they all pass. So we have a working implementation of a binary tree node. So it allows us to create the node, store data in it, and have a left and right side pointers to some subnodes. And it has an insert method that allows you to insert a value in the tree, and it will end up in the right spot. So this is pretty much all we need in terms of the data structures uh, core core thing that we need. But the test wants us to implement just another thing, which is an iterator. So this is probably the most difficult part in this exercise, because implementing an iterator is probably not necessarily what a lot of people do in C++. You don't implement data structures too often in C++ because usually you just use the ones provided by the standard library, so you don't have to implement your own iterators. But tonight we'll have to do that, because the last test is actually a test that calls a method called test sort. So I'll just enable one test here that can sort. And the test sort method accepts a pointer to the tree node, to the root node of a tree, and it tries to iterate it. How? Using what is a for each statement. It's a for statement, but that actually iterates the data structure. So how does it do that? it does that by trying to use a begin and end method on the data structure to fetch an iterator and increment it. So it fetches the begin iterator, and it increments it until it reaches the end. And at every point, it dereferences the iterator to actually fetch the value. So we'll have to declare an iterator class. So let's do that here. What I'll do is that I'll declare a forward declaration for the iterator that I'll call const iterator, because it's an iterator that does not allow you to modify the tree, because it doesn't allow you to modify the values. So by convention, in C++, we usually call those iterators const iterators. And I will add two new methods here called begin that returns a const iterator, and one called end. So an iterator is basically just an object that points to a specific spot inside the data structure that we're implementing. And an iterator allows you to it can be dereference like a pointer would to fetch the value it points to, and it can also be incremented to go to the next iterator. Some iterators can actually be decremented when they are bidirectional iterators, and yet other iterators called random access iterators can be incremented by a specific number of spots. But for our own data structure, all we need to have is a forward iterator, meaning the very basic minimum implementation needs to support incrementing the iterator. So implementing the various types of iterators is a more advanced concept that I won't delve into all the iterator types here, but I'll just showcase the implementation of one that is needed to make these tests pass. So what we'll do is that we'll define a class called const iterator, and in order for an iterator to work, there's a convention that it needs 5 specific inner types that allows others callers to access what type of value that the iterator returns. So I'm going to define them here. The first one is called value type, and it's a type that should be defined as the type of element that will be returned when you dereference the iterator. So here I will define it as a const t value, t being the type of value that is stored inside the binary tree. Why is it const? Because since it's a const iterator, we don't want to modify the value, so we write it as const. And then we have types called pointer. I can't type tonight, it seems. A pointer is just a pointer to do a value type. And we have one called reference, which is a reference to the value type. So these are just conventional. It's not necessarily required for the tests to pass, but usually when you define an iterator class, you will define these. Now there are two more types that are usually defined in an iterator. One is called difference type. The difference type must be the type that would represent the distance between two iterators. So usually what we do here is that, I'll just include this header here. We use a type from the standard library, which is called ptrdiff-t. ptrdiff-t is the standard type that represents the distance between two pointers in memory. So we can use the same type for our own iterator because our iterator is compared to another, the distance would be expressed as a distance between two pointers. In our case, it will not be used, but it's a good idea to know about this. And the final type that we need to define is called iterator tag. And we've defined it as forward iterator tag, which comes from the standard library and is defined in the iterator header. So what is iterator tag? It basically identifies the type of iterator that you implement. As I mentioned before, there are many types of iterators. A forward iterator is an iterator that can be dereferenced and incremented, and that's it. It does not allow you to have any other functionality. And there are others, bidirectional iterators that can be incremented and decremented, etc. And why are we defining an iterator tag is that some algorithmic functions in the standard library actually use the iterator tag to select a proper path, a proper implementation of an algorithm based on whether or not your iterator meets certain conditions. Like, for example, if you have a random access iterator that allows you to skip certain spots, you can go faster by just incrementing the iterator. But if you have a forward iterator, you have to increment it one by one. So that's the reason why we have an iterator tag that is usually defined. So if you don't define it, some algorithmic functions in the standard library will not be able to accept your iterator type. Okay, now that we have our types, let's see what we need to store in an iterator. So what we actually need to store is just a pointer to the current node that the iterator points to. So we'll store it as a pointer to a binary tree. Let's call it not this way, sorry, node. So here, the and we'll initialize it to null PTR initially. So every iterator will store a pointer to the node that is currently being the current node in the iteration, in the enumeration. And when we dereference the iterator, we'll use the node to fetch the data that it points to. So we'll define two constructors inside the iterator. The first one is the default constructor, which does nothing. And we need another constructor to be able to pass the binary tree pointer. But that second constructor is not necessarily meant for public use. So we'll define it as a private constructor here. And we'll pass a binary tree reference to a node. And this constructor will initialize the node pointer to the address of the binary tree that is passed in, like this. So we have basically a public constructor that constructs an iterator that points to nothing, and a private constructor that allows us to construct our iterator with a specific node. Now, we're missing only one thing here to be able to call that constructor, is that the private constructor in const iterator is not visible from the binary tree class, because in C++, inner classes, so classes that are defined inside other classes like I'm doing here, can access the private stuff in its parent class, but not the other way around. So what I'll do here is I'll declare a friend declaration, and I'll say that the binary tree class is a friend of the const iterator class. And a friend declaration in C++ allows the friended class to call your inner private methods and protected methods also. But so now that we have that, So the iterator doesn't do anything yet, but we can actually implement our begin and end method in the binary tree. So in begin, what we'll do is that we'll return a const iterator initialized with ourselves. And for the end iterator, we'll return a const iterator that is, sorry, I'll just change these to, that is default initialized, meaning it's called the default constructor, and initialize the pointer to null PTR. Basically, what the begin and end method means in C++ is begin is supposed to return an iterator that points to the first element of the enumeration, and end needs to return an iterator that is one past the last element of the iteration. And the end iterator cannot be dereferenced. It represents the end of the enumeration, and you cannot dereference it. If you try to do so, you will either get an exception thrown or perhaps an error at runtime, but it won't work. So here, what we do is that to represent our end iterator, we simply create an iterator without a node that is pointed to, which will signal the end of the enumeration. Now, there's one thing we can change before going on is that since our default constructor here in const iterator actually does nothing because the node pointer is actually initialized in the private section, we can actually default it. We write it like this. So equals default tells the compiler that the default implementation of the constructor is good enough. So it will just generate it for us and just initialize all the member variables to their values that are specified in the code. And that's it. Now, inside the iterator, the first thing that we have to do is that we have to implement a way to fetch the value that is pointed to by the iterator. And for this, we need to define to override two different operators, which is the star operator and the arrow operator. So the star operator, which is declared like this, should return a reference to the element that the iterator points to. And we can use the reference type that I declared earlier. So we'll say it's return a reference. And what we do to implement this is we use the node that is stored inside the iterator, and we call its data method. So this will fetch the data inside the node that is currently pointed to by the iterator and return a reference to its inner data. Now we have another operator that we need to implement, which is the arrow operator. So in C++, when you dereference an object with a star, it will call the operator star here, the dereferencing operator, if it's defined for the type. So that's the way. The operator keyword here is the way to actually override a specific operator for a type. So you say that when somebody tries to use the star or the arrow operator on my object, I want it to call this function instead of doing the usual thing that the compiler would generate. In our case, if we did not override the operators, it would not compile because there's no default implementation of these for a specific type. And the arrow operator is basically the same thing as the star operator, but instead of returning a reference, it actually returns a pointer to the element inside the iterator. So we could do this in two ways. We can either use our node pointer here, or we could implement the arrow operator in terms of the star operator. How? first we fetch a reference. Let's add a return first. We fetch a reference to this, which this is a reference to the iterator. We call its star operator like this, and we take the address of the returned object like this. So this is a bit tricky. This is a bit weird to look at. But what this actually says is take the this pointer, dereference it once to get a reference to the iterator, then dereference it again to call the operator star override that we have here. And let the little and sign here says to take the address of that and return a pointer to what is reference. Okay, so next step in our implementation of our iterator is iterators need to be able to be compared to each other. So what we need to do so is we need to override the equal and unequal operators in order to compare two values of our class. So let's do that. So again, we're using the operator keyword here, and we're overriding equal equal. This time the operator takes an argument, which is the right hand side of the equal equal. So basically, when you override the operator equal equal inside a type, the object of that is being compared will be passed as the left hand side of the operator, and you received a reference to the right hand value here. So let's call it other. So this function returns a bool, and it needs to say whether or not two iterators are equal, meaning does those two iterators point to the same point inside the enumeration. So this is easy for us to know. We just have to compare our node pointer to the other iterator's node pointer. So if our node pointer is equal to the other iterator's node pointer, then they are at the same point in the iteration. Now, when we override the operator equal equal, this doesn't automatically provide us with an implementation of the unequal operator. Unfortunately, I'll on in the C++ language that we're using here, so we have to override it also. So that will override the unequal operator. So it's basically the same signature. And now we want to know whether these two iterators point to different spots. So one way to do that would be to write the same code as before with the node pointers. But one trick that we can use, it is usually recommended to do so, is to actually use the implementation of the equal operator. So what I'm doing here is that I'm saying call the equal operator on the two values and negate it. So the sign here says to take the opposite of that. It's a not operator, sorry. Now, just before we move on, just one remark. In the C++ 20 version of the C++ standard, they actually added a new feature to the language that says that if your operator equal is defined for a type, but not the unequal operator, the compiler will automatically generate a version of the unequal operator that is similar to the one that I just wrote. Unfortunately, this is only available in the C++ 20 version of the standard, and in Exercism, we target C++ 17, which is a previous version of the standard. So this makes sense because new versions of the C++ standard are not necessarily implemented at the same pace in all compilers. So in targeting the C++ 17 standard in the Exercism C++ track allows more people to actually use the track with the compiler that ships with their system. So I understand why they're doing this, but here it makes us work harder because we have to override the operator unequal ourselves. Okay, moving on. Now, what we want to do here, there's only one piece missing inside our iterator, and it's the increment operator. And in fact, for an iterator, we have to implement two increment operators, and I'll explain why after I write this. So basically in C++, when we increment a value, you can do it two ways. You can use the prefix increment operator like this, like plus plus value, or you can do it with the postfix operator, which is value plus plus. For people coming from languages that do not have a distinction between these two types of increment and decrement operators, the way it works in C++ is that when you call the prefix version, it actually increments the value and returns the new incremented value. And if you call the postfix version, it increments the value, but actually returns the previous unincremented value. So it works a little differently. So we have to do this in our iterator class, and we have to emulate this behavior. How? It's pretty easy when you know how to do it, but so I'll first start by defining the first operator plus plus, and this one is the prefix version. And this returns now the plus plus operator needs to return an iterator pointing to the new point after the incrementing. So we can just return a reference to ourselves because we're incrementing the iterator here. So I'll just add a to do here. So we'll have to actually implement the increment here. And afterwards, I'll just return a reference to this. So we'll discuss how to implement the plus operator after that because it's non-trivial. It's actually non-trivial. And then we have to implement another increment operator, which is the postfix operator. And by convention, the postfix increment operator actually takes another argument of type int, which is actually never used inside the method. I don't know whether it's defined or not what you receive in that argument, but it's not important. You don't have to use it. You just have to declare it to differentiate between whether you're overloading the prefix or postfix operator. So the postfix operator returns the point in the enumeration that was before the increment. So we have to increment the iterator and return an iterator to the previous point. So this is actually easier to do than it looks. So what I'll do here is I'll declare an iterator that copies this. So this line here declares a variable called it that is a copy of the current iterator. And the auto keyword tells the compiler to deduce the type of it based on the expression. So here it will deduce the type of it to be of type const iterator. After I do this, I can actually call the prefix increment operator like this on the current iterator. And then I can return the iterator that I copied earlier. Now, you might wonder, when I copy the iterator here, what constructor will that call? So actually, this will call the copy constructor of our iterator, and we have not defined any. So it will generate a copy constructor for us, which will simply copy the currently pointed node. That's good enough for us. So we're not going to define a custom copy constructor in our iterator class. But if we wanted to do something else, we'd need to define it in some other way. Okay, so basically here, to implement the increment operator, we can be in one of two situations when we want to increment the iterator. The first situation is inside the pointed to node, is there a right node or not? So if the node that we're pointing to has a subnode to the right, then we want this iterator to drill down and point to the right node because that's the next step in the enumeration. So this is easy to do. So we'll say that node equals node dot right, and I'll say get here. So this fetches the right node, which is stored inside a unique PTR, and the get method of the unique PTR returns the actual pointer that is stored inside the unique PTR. So we say if we have a right node, drill down to the right node. This is easy. This is easy. But now, what do we do if we don't have a right node? Now we have a problem because if we don't have a right node, we actually have to backtrack to our parent node and keep backtracking until we reach a point where we can go down another path. So this is pretty tricky to do currently because we do not have a reference to our parent node inside our nodes. So in order to implement our iterator, we'll have to add that. So here in the binary tree structure, I will add a new variable that is called parent, that is a pointer to the parent node. Let's initialize it to null PTR initially. And what I'll do is initially when the binary tree is constructed, it will not have any parent, which it makes sense because when you're constructing the root, you don't want the parent to be set. But when you call the right, when you actually create a leaf, create a new node to insert somewhere, you actually have to save its parent. Like this. So when we create a new binary tree node here with our data to insert, we say the parent of the new node will be this node. And we do the same thing if the code is for the left node. So this here will actually give us a way to let enumerate our data structure because we can drill down the child nodes and we can actually go up to the parent nodes. So this is less trivial, but what we need to do here is that so going back to the const iterators increment operator, when we're pointing to a specific node, we have to go up to the parent and keep going up until we either reach the root or we reach a point where we followed the left path. Then we've reached our proper thing. So how do we do that? So we say while our pointed node is different from the null PTR and our pointed node right node is equal to this to node, sorry. So here the situation is if we have a pointed to node, And sorry, I missed something here. If the node we point to, if the parent of our node is actually set, so if we have a parent node, if our node has a parent and we follow the right path, meaning that our node is actually at the right side of the parent, we have to go up one level. So we say node equal node arrow parent. And once we reach a point where this is no longer true, we've reached a point where we actually need to go up one parent and we've reached the node that we want. Here. So this might feel non-trivial. My goal was not necessarily to describe it exactly how you want to implement a binary tree. I just wanted to point out how to do it in C++. So I'm not going to spend too much time explaining why we're implementing it like that. So here we go. So here we should have a working implementation of the increment operator, which will allow us to actually iterate our values. But there's just one thing that doesn't work. It's this constructor here doesn't really work. What we do is that when we construct a const iterator, we pass it the root node here, and we just start at the root. But this is incorrect. So what we need to do is we need to start at the leftmost node that is inside the tree. So how do we do that? Let's declare a helper function to do that. That will be called leftmost. So the leftmost helper will receive a reference to a binary tree and will return a pointer to the leftmost node inside the structure. So basically what we want to do is we want to start at the node and go down the left node and keep doing that until we reach a point where there's no longer any left node and we've reached the first point in the enumeration. So I'll declare a pointer here that is the address of the node that we receive, and I'll say while the node has a left node, follow it. And then I'll return the pointer to the final node that we've reached. So we need to use that method here when we construct the iterator, meaning that we'll call it here with the node we receive, because we need to start at the leftmost spot inside our version. And then we actually have to use it in one additional spot, meaning that when here in the increment operator, when we follow a right node, we actually have to drill down to the left too. So I'll just say here called leftmost with the node that is to the right. So we drill down to the right and then we drill down to the left until we reach the bottom, and then we're at the proper spot. So this should end our implementation of the iterator and should give us a way to iterate. So if we go back to the test, now we have enabled a single test that iterates a single value. So let's build our code and see if it builds and if it runs. So it doesn't build. I forgot something. Oh, I forgot to write a return value here, a return statement here. I just wrote node arrow data, but I forgot the return, sorry. So let's build again. It builds and it actually works. So to validate that our enumeration is correct, that our iterator was implemented correctly, we can actually, or we can actually enable all the tests and see if it works. It works. So there we have a working implementation of our binary tree. It allows us to explore the tree by following the left and right nodes. It allows us to actually insert values inside the nodes, and it allows us to iterate the entire tree structure from beginning to end in sorted order using our const iterator. So that was quite there's more than 100 lines of code here, which is quite a lot for an exercism exercise. So that's the the minimum implementation that I wanted to showcase. There are other things that we could do to improve on this solution. I will try to mention some of them quickly here, but just for those of you who are content with having a working exercise solution, this is a working exercise solution. So you could easily take this and submit this to Exercism, and it would pass all the tests, and you could publish it as your solution. So, but there are a couple of things that could be improved. So I'm going to just mention them here really quick before I end the stream. So the first thing that we could improve is that the data that is stored inside a node could actually be a const value like this, because we don't want to modify the data once it's inserted inside a node. So if we declare data to be a const value, that actually offers us a protection from being accidentally able to modify the data somewhere. So if we build this, we should see that it still compiles and runs fine, which it does. So this is the first, let's say, improvement that I wanted to point out. And there are other improvements that we could point out. The first one being here, the constructors. So in C++, it's usually a good idea that if you write a constructor that takes a single parameter, or that can be called with a single parameter, so it can have other parameters with default values, you should mark it as explicit. Now, what does explicit mean? Explicit is a keyword that basically tells the compiler that it's impossible, it shouldn't allow code to implicitly convert a type into another type here. So basically what I'm meaning here by adding explicit to that binary tree constructor is I'm telling the compiler that whenever there's a function that accepts a binary tree value, you cannot pass in a value of type t and implicitly convert it by creating a binary tree instance and passing it along. So this is how C++ normally works. When you call a function with a value that is not what the function takes, you want it will try to do an implicit conversion. Sometimes it is useful, like when you write a function that accepts a string object, you can call the function and pass it a string literal, and it will actually do an implicit conversion and create a string from that string literal. So that's useful for an object, like for a class like string. But for objects like data structures, this can be a little bit weird. So usually we want to try to avoid having implicit conversions in those cases. So since the implicit conversion is the default behavior, we have to tag our constructors with explicit here. And the constructor in our iterator could also be tagged with the explicit keyword here. So that's one improvement that we could do. And there are others that could be done. They are a bit more obscure, but I will try to mention them. So here, our binary tree is sorted in ascending order because we're using the less than operator on the data that is passed in. So it will only work, it will only produce a tree that is sorted in ascending order according to the less than operator for your type. But it can sometimes be useful to create data structures that are sorted in other ways. So a convention that is used in the standard library is that for containers and data structures that uses comparison operators, instead of using the comparison operator directly, you actually declare another type parameter for your class. I'll add one that I'm calling compare, and then I'm going to declare a default value for that type, which is std less t. This is actually in the functional header. So what is std less? Std less is a predicate that accepts two values of type t and will call the less than operator. So it's basic, it's pretty basic, but what it allows us to do by having the type of compare the predicate to compare the elements as a template parameter, it would allow us to actually create a binary tree that would be sorted differently. So for instance, we could pass std greater, which would call the greater than operator, and it would sort the binary tree in the opposite direction. So now that we have our compare type name, the only thing left is to actually use it. So here in insert, instead of calling the less than operator directly, what I'm going to do is that I'm going to first create an object of type compare using its default constructor. I could also write it like this. And then I'm going to call its parenthesis operator. So this, it's basically the operator that allows you to have an object act like it's a function and pass the two values as before here. So here, the code is pretty similar, except that we use the compare object to compare the two values. So if I build and run the tests, because there's a default value for the compare type, which is less, it will still work and all the tests will still pass. But if I wanted to, I could add another test with which sorts in the opposite direction, and I could see that it will sort in that order. Now we're running a bit late, so I don't think I'm going to delve too deeply into the last improvement that I wanted to showcase, and it was the use of parameter packs to write a function to actually create the data inside by calling a constructor with a variable number of arguments. But maybe you can look it up, and as it's documented as being in the documentation is referred to as a parameter packs. So if you want to look it up, you can look it up in documentation like cppreference.com. So it's getting a bit late, so I don't think I'm going to showcase that because it's a bit long to explain. So, but there you have it. So we have done a lot of things tonight. We've used smart pointers, unique PTR. We've declared templates. We've declared an iterator, which was called const iterator, and then we've implemented the iterator concept, the forward iterator concept correctly. So all in all, this is one way at least to implement the binary search tree exercise in the C++ track. So it would also be possible to use binary tree pointers directly for the left and right pointer and to override the destructor to properly deallocate the left and right nodes if we have them. So that would work also, but using smart pointers is usually cleaner because it's safer, because if you forget to actually override something or deallocate something in your destructor, you don't leak memory because Using smart pointers like unique PTR is what is called in the C++ jargon. It's called RAII. Resource acquisition is initialization. So meaning that you basically initialize a smart pointer and you pass it and you pass it a value and it acquires the value. That's what it means. So this is a principle that is used quite often in C++, and it allows you. Okay, there's a good question here in the chat. So the question is, would it really work without smart pointers? The tests require left and right to return references to unique PTRs. That's a good question. Uh, I'm not sure that it does. What it does require, however, here, if you check out the method that is called test leaf in the tests, it actually, when you dereference left and right, it casts that to a bool and assumes that this would work. So I'm not entirely sure if the compiler would let you cast an actual pointer to a bool. Since it's a C-style cast, most likely it would, but I'm not sure. So we'd have to try it. But it's a good question. So yes, the tests are indeed written in the optics that we're going to use a unique PTR pointer to store our left and right node. But depending on how the tests are actually written, it would be possible to implement the binary tree without smart pointers. But indeed, if the tests do not accept it, it wouldn't work. So I was just wanted to mention it uh, as a way to say that it's possible to implement it directly. But even then, the tests kind of assume that you're going to use smart pointers, the unique PTR pointer, and it's a good idea to do so. So I think that it's a good idea that the exercise actually expects you to do so, because that's a good practice to have anyway. So there, we're going to be ending the stream pretty soon. So thank you for joining me tonight. This has been entertaining, even though I made a couple of silly mistakes here and there. So this will probably be my last C++ stream for the month of March for Exercism. So if you are interested in more C++ knowledge, I encourage you to check out the C++ track on Exercism, which has lots of different exercises that allows you to practice your C++ knowledge. And it also provides a couple of good references to sites like cppreference.com, which is a very good site for a reference for the C++ language and its standard library. So thank you for joining, and have a fun night. Bye.